All right, so when we talk about reactions in the lab, we got to kind of look at reality. And the reality is, when we do a reaction, it is very, very rare to get as much product as what the theoretical yield says that we should get. And that's for a wide variety of reasons. A lot of it is user technique. If your technique's not great or you're spilling stuff all over the place, you're not working up your reactions properly, then that's going to decrease the yield. Another major factor is just the nature of the reaction itself. Not every reaction goes to 100% completion. In fact, that's kind of a rarity that you're going to get that, if your technique was flawless, that the reaction itself would make 100% yield. And I don't, we'll go into a little bit later why reactions don't work that way, why they don't automatically make 100%. But that's something we'll cover later, and kind of outside the scope of this lecture for now. But one of the things we do like to do is compare the how much we get in the lab to what we calculated before we set up the reaction. How much should we have gotten? And we call this percent yield. Percent yield is just a comparison of what you get to what you should have gotten. And so here's the formula. This is something you should just commit to memory. Percent yield is the actual yield divided by the theoretical yield. And then we multiply it by 100 to put it into like a percent. And the actual yield, this is something you get in the lab if you're actually doing the experiment. Or if you're reading like a story problem, you're doing your homework, this is something the problem generally gives to you. And the theoretical yield, this is something you calculate. Whether, again, you're doing this problem for a homework, you calculate it, whether you're doing this for lab. A lot of times what we as chemists will do is before we go actually do a reaction, we'll calculate it to calculate the theoretical yield to anticipate how much should we get. Um, and so that's something, again, that's something you calculate. So just to kind of do a quick example, and then we'll go a little bit more in depth. Um, so on our last example, we found that our theoretical yield was 10.4 grams of silver chloride. So I'll just kind of go back up here. So based on this problem, we could make at most 10.4 grams of silver chloride. Now we go into the lab, do the reaction, um, and at the end of the day, we weigh out only 8.4 grams of silver chloride. So what's our percent yield? Well, we're going to take the value we weighed out, 8.4 grams of silver chloride, divide it by our theoretical yield. Notice that the units will end up canceling out. This is a unitless value. And then multiply it by 100 to put it into percent. Again, since this is a calculation, you got to keep track of sig figs. So this comes out to 81%. Now, a couple of important things to note about percent yield. Over 100% yield is not possible. Think about that for a second. Why can you not have a mass of more product than the mass of the reactants you start with? Well, the law of conservation of mass. You cannot create matter. And having over a 100% and saying, oh, look at this, I got more than anticipated. No, the only way you can get over 100% yield is if you have something extra in there that you were supposed to get rid of. Like, let's say the solvent for the reaction, you didn't get rid of all of it. Or maybe you did some washing of the product with water and there's still a little bit of water left in. That's not product, that's unwanted stuff. and it contributes to the mass you weigh out, but it is not really truly the mass of the product. So don't be impressed if you ever do a reaction and you get 100% because that just means you did something wrong along the way. But the other thing I want to emphasize is don't be disappointed with yields less than 100%, because, as I said before, a lot of it depends on technique. And an even bigger factor, a lot of times, you could have a really good technique, but reactions just don't go to 100% completion. That's a very rare thing, as I said at the beginning. And it's something that we'll talk about a little bit later about why some reactions just don't go all the way to products. All right, so let's do a really in-depth example here. And so here's the question. So we have 10.4 grams of solid lead to nitrate, and we're going to add that to 66.9 milliliters of a 1.20 molar sodium iodide solution. So if we get 14.1 grams of lead iodide, what is the percent yield? All right, so we haven't done a problem like this, but I want you to kind of maybe pause the video, answer the question. What do we do first? Step one, what are we missing? A balanced equation. Okay, the problem here doesn't give it to us, so let's figure it out. Okay, so we're taking solid lead to nitrate. Okay, how do you find that? Well, make sure you remember how to do your nomenclature. So that's a solid. Then we're going to react it with sodium iodide. Sodium is Na plus, iodide is I minus, and the problem says it's a solution. Now, how do I know it's a solution? Well, I got a volume and a molarity. That's solution. Now, if you look at this kind of reaction, we're going to be doing one of those double replacements, meaning we're going to swap the cations. And so the iodine will go to the lead, and the sodium will go to the nitrate. Now, to kind of wrap this up, just to have it completely correct, we'll balance it. Look at your solubility chart. I know it's kind of from another unit. When you look at that, you'll see that sodium nitrate is completely soluble, but lead iodide will form a precipitate. Okay, so let's go through and balance this. If we look at the left, I have two nitrates. So on the right, I'm going to put that. Well, you say, well, that just threw off my sodiums. Okay, well, let's fix the sodiums. I'm going to put a 2 here. And that inadvertently balances out the iodine. So we're good to go. So this was our first step to get a balanced equation. Step 2, I need to find the limiting reactant. And in order to do that, use this age-old saying, get to moles. After that, I can figure out what my theoretical yield is going to be. And then finally, I can calculate my percent yield. All right, so let's get to moles for both of our reactants here. So let's start with the lead nitrate. We have 10.4 grams of lead nitrate. And what do I need to go to moles? I need the molar mass. So the problem gives it to us. 1 mole of lead nitrate weighs 331.2 grams. So that gets me to moles of lead nitrate. Now I want to get to moles of product. What do I use to do that? I'm going to use the coefficients from the balanced equation. And that's a 1-to-1 ratio. 1 mole of lead nitrate makes 1 mole of lead iodide. And now I can get to mass of lead iodide by using, again, the molar mass. 1 mole of lead iodide weighs 461.01 grams. And now our last remaining unit is grams. All right, so throw this in the calculator. Keep track of our sig figs. That comes out to 14.5 grams of lead iodide. Now, this does not mean anything. I have not finished yet until I do the same thing for my other reactants, because I have to figure out which one am I going to run out of first. The other reactant, though, is given, we're given solution. We're given a molarity and a volume. So let's start with that to get to moles. I'm going to deal with these milliliters because molarity is in units of moles per liter. The volume there is liter. So let's convert this to liters first. So 66.9 milliliters of the solution, 1,000 milliliters makes 1 liter of the solution. So that gets me to liters. Now, how do I get to moles with a volume? I use the molarity. That molarity means I have 1.20 moles of sodium iodide in 1 liter of solution. Okay, so liters of solution cancels out. Now I got to moles, so let's get to moles of the product. The balanced equation says 2 moles of sodium iodide will make 1 mole of lead iodide. And then finally, to get to grams of that product, I use the molar mass. All right, again, notice how the only remaining unit is grams of product. So I've canceled everything out correctly, plug this into the calculator, and it comes to 14.5 grams of lead iodide. So what does that tell you? That tells you the lead nitrate is the limiting reagent. And 14.5 grams of lead iodide, our product, is the theoretical yield. Now we have everything we need in order to calculate percent yield. Because percent yield is the actual yield. So this is what was weighed out in lab at the end of the day, divided by the theoretical yield, which we just calculated. We'll multiply it by 100. So the problem says that we got 14.1 grams of lead iodide. So that's our actual yield. And our theoretical yield we just calculated was 14.5 grams. And then we're going to multiply that by 100 to put it into a percent. And that comes out to 97.2%. Right, like always, like I usually say almost at the end of each of these sets of lectures, the only way that this is going to become second nature is if you practice. There's already practice problems up on Canvas for this, so I highly recommend taking the time to look at those as well as going through the homework.